Another example. So we have another example, and we're going to apply what we learned today. Exact ODE. So question says, solve the following. You have dy over dx equals to xy squared minus cosine x times sine x divided by y times 1 minus x squared. Okay, very well. So you should be asking if it's separable in step 1, then move to step 2, apply the appropriate method. Okay. So can we separate these? If I multiply everything by dx, well, how should I separate xy squared and cosine x sine x? So it seems like it's not separable. What about linear? Is it linear? So y prime is equal to, if you separate these fractions, then here you have x, y squared divided by y, 1 minus x squared. It means that you end up with x times y divided by 1 minus x squared. So so far we don't have any issue, but on the right hand side, what you get cosine x sine x divided by y times 1 minus y x squared. And then, so this is another issue on the right hand side. And if you flip this and try to write it in terms of x equals to a function of y, then you end up with cosine x sine x, and we cannot write this in a linear form. So it seems like it's not linear as well. What about exact? Is it exact differential equation? Let's check to see if it's exact or not. So let us check if it is exact or not. Remember the definition of exact differential equation: m of x and y dx plus n of x and y dy is equal to 0. And then, as we know, the partial derivatives of m and n exist on a rectangular region. We need to see if the partial derivative of m with respect to y is equal to partial derivative of m with respect to x, with partial derivatives continuous on a rectangular region like R. Okay, so first let's write it in exact in the differential equation that we can check to see if it's exact or not. So here you get just pure algebra. Just do algebra here and then write it this way. X y squared minus cosine x sine x dx, and then let's bring the rest of it to the other side, minus y 1 minus x squared dy equal to 0. So here we see we have our m, and here we have our n. Okay, let's just distribute this negative sign here, x squared minus 1. This is our n. Now take the partial derivative of m with respect to y. It gives you 2xy, and this is going to be just 0. And partial derivative of n with respect to x, this guy is going to be, well, here you get y times 2x, so 2xy. So as you can see, they are equal to each other. So the condition for being an exact differential equation is met. It is exact. So since it's exact, we should be able to apply the method to find a solution for an exact differential equation. Now, find the solution. Very well. To find the solution, we know that that function exists, f of x and y is equal to the integral of m dx. So this is our m, x y squared minus cosine x sine x dx. And by solving this integral, f of x and y is equal to, with respect to x, you get a half x squared y squared. And here you can combine these two, or you can use a substitution. So if x is equal to, if u is equal to sine x, then du is equal to cosine. So you get minus a half sine squared of x plus gy. So far, so good. Now let us move on to step 2. In step 2, we get the partial derivative of f with respect to y equals to a. So let's take the partial derivative of f with respect to y. We get a half x squared 2y, so you get x squared y. And here you're going to have 0 because you're taking the partial derivative with respect to y. And then you get g prime of y equals to n. But what is n? N is just right here, y x squared minus 1 x squared y plus g prime of y equals to y x squared minus y. So as you can see, these two terms, they cancel out each other. We can solve this equation. G prime of y is y. So g of y is the integral of y, which is a half y squared plus a constant of integration. So in the last step, our solution general form is equal to, we found some part of it. Now we have our g, a half x squared y squared minus a half sine squared x plus a half y squared plus constant of integration. This is our general solution. If you have an initial value problem, then you can find the particular solution. So this is our general solution.